So I'm going to tell you about this joint work with Frédéric Jean, and the aim of the talk is twofold. In the first part, I will talk about Hausdorff volumes in sub-Riemannian manifolds and how the presence of a singular set affects these measures. And then I will focus on the behavior of such measures with respect to a smooth volume and show how to use its regularity to prove some results on measured Gromov-Hausdorff convergence. So first, I start with some notations. So a sub-Riemannian manifold, which is, I guess everyone is familiar with that, is a triple where M is a smooth manifold, D is a smooth distribution, which may be rank varying, and G is a Riemannian metric on D. So with a Riemannian metric, I can measure the length of curves that are tangent to D, and I can define the sub-Riemannian distance with the infimum of length of curves tangent to D. And of course, I assume the distribution to be Lie bracket generating. So at any point, so given a point P, there is a sequence of subspaces of the tangent space, which is called the flag of the distribution f at P, which is the sequence D1P, D2P, dr of P, P, which coincides with the tangent space, where di is the evaluation at P of vector fields that are Lie brackets of length up to I between elements of the distribution D. So D1, it is D. And also, I am going to need the dimension of these spaces, which I denote by NIP, dimension of the IP. So the manifold is called equiregular. If the function, all these dimensions, and I of P, is constant on M for every I. And otherwise, we say points at which this dimension is not locally constant are called singular. So examples of equiregular sub-Riemannian manifolds are Carnot group or contact structures, whereas a couple of examples of non-equiregular sub-Riemannian manifolds, example of non-equiregular are the Grushin plane, which is the sub-Riemannian structure on the plane defined by the span of two vector fields, which are the one, it is just the constant vector field d over dx1, where I take x1, x2 coordinates on R2, and the other is x1 d over dx2. So here, the dimension which varies is already the first one, because I have n1 of x1, x2 equal to 2 for x1 not 0, or 1 at x1 equals 0, and n2 is always 2. And the other example is the Martinez space, which is the sub-Riemannian structure on R3 given by the span, where I declare this to be an orthonormal frame, so I choose the metric G for which this is the orthonormal frame. x1, x2 with x1 again d over dx1, and x2 equal to d over dx2 plus x1 squared over 2 d over dx3. So here the first dimension is constant, x1, well, let's say of x. It is equal to 2 for every x in R3. And the second one is the one which varies, and it is 2 at points, it is 3 at points where x1 is not 0, and it is 2 on the x1 equal to 0 plane. And the third, it is always 3. So these are two examples. And also another notion I will be needing is the one of Hausdorff measures on a sub-Riemannian manifolds, which are measured depending on a parameter, positive, which are defined in this way as the limit of epsilon goes to 0 of the infimium of sum of diameter Si to the power alpha, such that E is covered by this countable covering, where Si are just subsets of M, not empty, and they have diameter less than epsilon. This is a standard construction in metric spaces. And I can do the same construction, which I call spherical Hausdorff measure, where I require, moreover, that these Si are balls. And for every E, there is a notion of Hausdorff dimension, which is, so for every set E, there exists a limit value alpha bar, such that H alpha of E is plus infinity before alpha bar and 0 afterwards. And at alpha bar, everything can happen. And alpha bar is called the Hausdorff dimension of E. This is just by construction of the Hausdorff measures. Also, another notion of measure I will use is the one of smooth volumes on M, on oriented manifolds M. So I assume M to be oriented. I take an undegenerate N form, and I define a smooth volume as the integral of this form. Right, so the first part is about Hausdorff volumes. So by definition, the Hausdorff volume on a sub-Riemannian manifolds is the spherical Hausdorff measure corresponding to the parameter here, which is the Hausdorff dimension of the manifold. This is by definition the Hausdorff volume. So what I'm interested in is to see if this is a smooth measure and how I can compare it to a smooth volume. So the equiregular case is well known. And what is known is the following, that first, this Hausdorff dimension of a sub-Riemannian manifold can be computed algebraically using the flag of the distribution as the sum over I of I Ni of P minus Ni minus 1 at P. and these number are constants by assumption here. Also, this the Hausdorff volume, which so I will denote this number Q. The Hausdorff volume SQ is a Radon measure on M, which means it is finite on compact sets. It is absolutely mutually absolutely continuous with respect to any smooth volume. So this means that so SQ is absolutely continuous with respect to mu, and also mu is absolutely continuous with respect to Q. And so this means that they have the same sets of measure 0. And I can compute the Radon-Nikodym derivative of SQ with respect to mu as follows. So dsq over d mu at a point Q can be computed as a density, that is, can be computed as a limit for epsilon goes to 0 of the quotient of the Hausdorff volume of a ball, of a small ball centered at Q, divided by the mu volume of the same ball. And this limit coincides with 2 to the power Q divided by mu hat Q of B hat Q. So what is this object? B hat Q is the unit ball in the nilpotent approximation of the sub-Riemannian manifold at Q. And so the nilpotent approximation, we know it is the tangent space endowed with a sub-Riemannian distance, which I denote by d hat Q. And this is the unit ball for this distance. And mu hat Q is a smooth volume on TQM, which is canonically associated with the volume measure mu. So this theorem is due to the algebraic characterization, and the absolute continuity is due to Mitchell. And the fact that this Radon-Nikodym derivative can be computed as a density is a consequence of the differentiation theorem for Radon measures. And this computation, the fact that this equals this, was done by Agrachov, Barilari, and Boscain. So what happens in the non-equiregular case? In the non-equiregular case, the manifold M splits into two sets, the set of regular points and the set of singular points. So here, these are points at which locally the dimensions are constant. The set of regular points, it is an open set. And what can we say about the Hausdorff dimension of M? Well, it is the maximum between the two Hausdorff dimensions of the set, of the two sets. So for this one, we have the algebraic characterization, so we know how to compute it once we know the flag at regular points. This also admits an analogous algebraic characterization, which I'm not talking to you, which I'm not telling you, but if you want, I can do. Characterization under some stratification assumption. And so this is to say that we know how to to compute this dimension. So we know who the Hausdorff volume is, and so the fact. So how we can use that result in the non-equiregular case? Well, we can say we can, so I will denote by QR the Hausdorff dimension of the regular part, which is the maximum of Q at a point Q when Q is in R, where this Q of Q is the one over there. Okay. So, and now I want to apply that result over there on the regular part. So what can I say is that if I consider the spherical Hausdorff measure with parameter QR restricted to the singular set, this means that, so the measure, this is a notation, standard notation, a measure restricted to a set of A is nu of A intersected E. So what can we say is that when the singular set has measure 0, this measure over here is absolutely continuous with respect to a measure mu. And the density, again, at points Q, which for Q at which the algebraic number over there is maximal, this guy is, again, this fact, the 2 to the power QR divided by mu Q. For Q in R, of course. Okay, and so this is somehow applying this to a connected component of the regular sets where the dimension is maximal. And thanks to this fact, I can give say something about the Hausdorff volume in M as follows. So I can say that corollary. So I denote by vol H the Hausdorff volume on M. So let's regroup the results. When the singular set is empty, we know that the Hausdorff volume essentially behaves as mu, as a smooth volume. When it is not empty and has measure 0, there are three possibilities. Either the set of regular points has dimension greater than the set of singular points, either equal, either smaller. And in this case, so if somehow the regular part wins over the singular part, again we can say this. If they are equal, the Hausdorff volume splits into, admits a Lebesgue decomposition. So it splits as this sum. And this is the absolutely continuous part with respect to a smooth volume, and this is the orthogonal part, the singular part. And when the last inequality is realized, then the Hausdorff volume is completely singular with respect to a smooth measure.
Supported by the singular.
I'm sorry?
Supported by the singular part.
Yeah. So here, remember I'm saying that the singular set has Hausdorff dimension greater, strictly the greater. Okay. So in the examples I gave you before, what are these measures in the Grushin plane? So if I take, for instance, as the smooth measure the Lebesgue measure, then the regular points are points at which x1 is not 0, and the Hausdorff dimension at regular points is 2. And well, we can also compute the Hausdorff dimension of singular sets. It is also 2. And right, so I'm saying, so in this case here, the Hausdorff volume is just the spherical measure S2 with respect to the distance. And in Martinet case, we have, taking again the Lebesgue measure in R3, the regular points are those at which x1 is non-zero. And here the Hausdorff dimension is 4. And also we can compute the Hausdorff dimension of the singular set, which is again 4. So this Hausdorff volume is S4. And both cases are in here, in this situation here. So we have 2 parts. 2 non-trivial parts.
And, in this case, the singular part of the measure is smooth with, if S is a manifold, then the singular part is smooth with respect to a smooth measure on this sub-manifold.
Yeah. Or with with the Lebesgue measure on the good Lebesgue measure on the so for instance here it is a plane, so this measure is somehow something like a 2-dimensional Lebesgue measure.
You could have some smaller strata and then
yeah, I can go further in the stratification. Yeah, in this case the singular set is only 1 strata. Okay, now I want to focus on this measure here, on this SQR. And I want to say, and I want to see how the presence of a singular set affects this measure. So the main result is the following. Is that if I take a connected component of the regular set at which the Q of Q is equal to QR, so having maximal Hausdorff dimension, then for every compact set in M, there exists a constant, Ck, greater than 1, such that the Radon-Nikodym derivative of this measure with respect to a smooth volume at a point Q can be pinched as Ck over nu of Q, and here as 1 over Ck nu of Q for every point Q in U intersected with K, where this function nu of Q is defined as follows. It is the maximum of the absolute value of omega xi1 xin at Q, where this omega is the one defining mu, is the one such that mu is equal to the integral of omega. And what are these vector fields here? The xi are an adapted basis for the flag at Q. So what does it mean, adapted basis? It means that the vector space so these vector fields are defined as Lie brackets between elements of a global basis for the sub-Riemannian structure, And saying that it is adapted at Q is equivalent to say that di at Q is the span of the xij at Q, such that the xij is a bracket of length less than I. So this is the multi-index that defines the bracket, and it has length less than I. So what do we get from this fact? What is this function nu of Q? So let's look for it in the examples I gave over there. So for Grushin, the pair x1, x2, they are an adapted spaces. So here I'm taking points Q in U intersected K. So the idea is, of course, if I take my compact set outside this, I mean, if my compact set is contained in the regular points, this says nothing. I mean, it's not interesting because we know that everything is smooth. But if my compact intersects the singular set, so for instance, in the Grushin, say I take something like that. So I need to look for adapted bases at points outside the singular set. And for instance, the one I gave, it is an adapted basis. So I can write this as 1, 0, and this as 0, x1. So my nu is some constant times absolute value of x1. So when I divide, of course, I get something which blows up as my point Q goes to the singular set. What I'm saying is here is that since this basis is adapted at points Q which are regular, when Q approaches the singular set, there is some dimension which drops. So these vector fields become collinear necessarily. So the main consequence of this fact is that I have a blow-up phenomenon of my density as Q goes to the singular set. Also,
sorry.
Yeah.
Here is always a measure of S equal to 0.
Yeah, in the two examples.
No, I mean. No, I'm just asking if you.
No, I'm thinking if to have this this pinching, I guess you need to get the pinching estimates like that. You need to assume that. No. Okay.
No, it's just on the regular set. So when we work on the regular set, we do no
Yeah.
assumption on the singular set. It's just what the absolute continuity first.
Yeah. Over there you need. Yeah.
And it's always non-integrable, or?
No, it made me throw this. In these examples, it is not.
Okay, but in general,
It can be integral. So this is this go further in the analysis, but I don't want to talk about this here. So but it is a good remark. So I'm saying this blows up. Okay, but still it could be that when I integrate it, even at compact set which intersect the singular set, I can get something finite. It depends. Here I do not. In these two examples, if I integrate this 1 over x1, I get something which blows up. Also, let me mention that the same property goes for the pop measure. So the pop measure, well, I'm not going to define it. Pop measure. It is a smooth measure P on the set of regular points, which can be defined using a suitable inner product space structure on the graded vector space associated with the flag. So it is a smooth measure by construction. And also it holds true that, well, it's not a corollary, it's independent, let's say. it holds true that the Radon-Nikodym derivative of pop measure at points Q satisfies the same estimate, nu of Q, CQ over nu of Q at regular points. So also the pop measure blows up. And to get this, well, there is this explicit formula by Davide Barilari and Luca Rizzi, and from this formula and our result here, we can get the blow up phenomenon. So this was for the first part. So up to now, I have said something concerning the qualitative, let's say, behavior of this measure SQR. But remember, I gave you at the beginning this formula, this explicit computation of the Radon-Nikodym density. So I said that the SQR of mu is equal to 2 to the power QR over this. So, and now I make a remark that this function here, as Q vary among regular points, this function is continuous. It's not smooth, but it is continuous. And now I want to tell you how to use this continuity to study measured Gromov-Hausdorff convergences. So, second part, measured Gromov-Hausdorff convergences. Convergence. Okay, I am in a sub-Riemannian manifold. What you know is that when we blow up the distance at a point, we have a limit. So if I take the sequence of pointed metric spaces M 1 over epsilon times the sub-Riemannian distance and any point P, we know by the worker by Belaish that as epsilon goes to 0, this sequence of pointed metric spaces, Gromov-Hausdorff converge to the nilpotent approximation on the tangent space. Okay? So this we do know. If P is regular or singular, it holds for every point. Now I'm studying measures on the sub-Riemannian manifolds, and there is a notion of convergence of metric measure spaces, which is the following. So let's take a sequence of metric spaces, x epsilon, d epsilon, measure metric spaces, m epsilon, p epsilon. So this is metric measure space. I'm going to say that these converge in the measured Gromov-Hausdorff sense to some x naught, d naught, m naught, d naught. If, well, I require the sequence of pointed spaces to converge in Gromov-Hausdorff sense. And what do I require concerning measure? I require weak convergence, which is the following. So I ask that for every positive radius, I can define a map f epsilon r from the ball with respect to the distance d epsilon centered at P epsilon of radius r to my limit space, a function which is the quasi-isometry actually that realizes this Gromov-Hausdorff convergence here. And the weak convergence is about measure is the following: f epsilon r, the push forward of the measure m epsilon restricted to the ball, weak converges to m naught restricted to the ball in the limit space. So by here the notation is that if I have a function f from a metric space to another, and I have a measure over here, the push forward of a measure is the measure of the preimage. Okay, so these are measures on the limit space, and I'm asking that the weak converge to the limit 1. So the result we prove is the following. Okay, now in the sub-Riemannian world, we know we have already this Gromov-Hausdorff convergence. And one would expect, okay, I take here a measure which is intrinsically associated with the distance. For instance, I could take the Hausdorff measure associated with this distance here. Well, it would be nice if this convergence would, it seems to be that it would go for granted. Well, this is not the case. Well, it is, but you need to do some little work. So the result is the following. At regular points, the sequence of blow-ups, so 1 over epsilon d, now I blow up any smooth volume. So I take mu, smooth volume, and I multiply here by 1 over epsilon to q power q of p. This converges in the measured Gromov-Hausdorff sense to what we expect, the tangent space with the nilpotent approximation and with the measure mu hat p 0. And also, we have the analog for Hausdorff volumes. So for the spherical Hausdorff measure of dimension q of p associated with the distance d over epsilon p, this converge in the Gromov-Hausdorff sense to what we expect. As with respect to here the spherical Hausdorff measure with respect to this distance q of p 0. Okay, some comments. Why are we interested in this kind of convergences? Because if I have this weak convergence of measure, I have a good expansion of the measure of balls. Namely, as a consequence, I get that if I take the measure of a small ball bq epsilon using the weak convergence, I can say the weak convergence implies that this is mu q hat q of b hat q times epsilon to the power q of p plus a small plus something which goes to 0 like this. And also, so for the second one, I get the same expansion. Q. I don't know why Q has become P has become Q here. It's not important. B P over epsilon equal to S Q plus. Okay. Another comment is that actually this convergence also for singular points. This doesn't. Well, this doesn't. The proof I'm going to give a sketch of does not work for singular points. So we don't know if it holds also at singular points. So this is okay at P singular. And the idea we use is precisely the fact that the Radon-Nikodym density here, so it is continuous with respect to a smooth volume. So I'm going to sketch the proof. The idea behind the proof. So we already know I have to put this this is already done. Let's go to the second. So I want to define a function, a function f epsilon from the ball with respect to the distance d over epsilon, pr to tpm. So if I identify the tangent space using privileged coordinate, I will define f epsilon of x as I blow up the point x. Delta 1 over epsilon of x, where delta lambda are the non-homogeneous dilation. So the hypothesis approximation, that space TPN endowed with the head distance, it is homogeneous with respect to this non-isotropic, let's say, dilation. And what I do is that I take a point and I blow it up with a parameter 1 over epsilon. So what do I have to prove? I have to prove, so let's call this measure over here. I call it mu epsilon. Oops. Mu epsilon. So now I'm taking m epsilon to be mu over epsilon to the power q. So I need to prove weak convergence means that for every continuous function, I need to prove that the limit for epsilon goes to 0 of the integral over tpm of h d mu epsilon equals to the integral over tpm of h d mu hat p restricted to the ball. Okay. So how can we do this? Right. So I start by the beginning. H of x, d mu of x. This is equal to. Now I use the fact that mu epsilon is the push forward with respect to this map here. So I can use the change of variable formula and say that this equals to the integral over the ball for the distance d over epsilon p radius r of h delta 1 over epsilon x d mu of x divided by epsilon to the power q of p. Then I do a trick and I say that the set BD over epsilon PR as a set of points coincides with the set B with respect to the ball with respect to the distance BD of radius R epsilon. So I put here BD PR epsilon. Also, I use the fact that using the ball box theorem, we can nest. Thank you. We can nest this ball between two balls with respect to the nilpotent distance of radii R epsilon 1 plus small o of 1 with respect to epsilon, of course, and here same thing. Okay, so basically what I'm saying is that this integral, when I do the limit as epsilon go to 0, I can integrate this function either on this ball or on one of these sets. So I get that this equals the limit as epsilon go to 0 of the integral b d hat 0 r epsilon 1 plus small o of the same stuff, delta 1 over epsilon x d mu of x epsilon. Why do I do this? Because now this set is homogeneous with respect to dilations. So now if I do the change of variable delta 1 over epsilon x equal to y, if I do this change of variable, I get the measure mu in this privileged coordinate is homogeneous with degree q over q of pi. So this epsilon will simplify. This is equal to the limit. So epsilon goes to 0. So let's say epsilon to the power q of p integral over b dp 0 r epsilon 1 plus 1 h of y. No, here I know I have epsilon any longer because I have dilated. H of y, and here, so if I write my measure in terms of my smooth measure in terms of the Lebesgue measure, I have omega, the differential form defined in mu, computed at the coordinate vector fields at the point x, the Lebesgue measure of x. So here what I get is omega d over dy1 omega d over dyn computed at delta where am I? Delta epsilon of y, the Lebesgue of y. And here now it is the key fact, the continuity. So now when epsilon go to 0, the set where I'm sorry, and there was that over. So this guy simplifies with this. When epsilon goes to 0, here the set where I'm integrating converges exactly to the small to the ball in the nilpotent approximation of radius r. And the function I'm integrating, this is continuous, but anyway, it doesn't depend on epsilon. This, as epsilon goes to 0, but it is smooth, so it goes to, so if I compute the limit, I obtain integral b dp 0r h of y omega over dyn at 0, d Lebesgue of y. And by computation, you can it is possible to see that this measure is exactly mu hat p d mu hat p of y. So I get what I wanted. And the key point is the continuity. So why does this expansion hold also for singular points? Well, if I define for singular points this measure like this, here I didn't use anything about regular points. So only this. So if I define the measure like this, I have a convergence. And let me maybe end by saying that, so for the spherical Hausdorff measure, doing some tricks as I did here, what I get here is this function times the derivative, the Radon-Nikodym derivative of S of the spherical measure, which I know to be continuous because I know it equals this 2 to the power q, and this function here, it is continuous. So I can produce the same argument, and then I have the effect that the limit measure is exactly the one I wanted. So, and I just end saying that we wanted to see what we could do for general Hausdorff measure, not spherical ones. But this problem is turns out to be more difficult, more intricate, because first, we do not have an explicit formula, and it is hard to find one for the Radon-Nikodym derivative of h, of the measure, Hausdorff measure h. Why it is hard to find it? Because to estimate the general Hausdorff measure, one needs to be able to control coverings of sets which are completely general. Whereas for the spherical one needs to use to estimate only balls, And the other fact is that even if we knew how to prove an explicit formula for the Hausdorff measures, we do not know if this formula gives us something which is continuous. So, and by the way, something needs to be done, because proving the measured convergence is not implied simply by the Gromov-Hausdorff convergence. So something needs to be done, but we don't know if this argument can be generalized. So thank you for your attention.